Girish,
Sir, good morning, sir.
yeah, good morning.
Sir.
So you can hear me?
Yes, sir. I'm able to hear you and see you, sir.
Okay.
So, we'll start in 10 minutes, sir.
Okay.
Oh, thank you.
Girish, actually, like these participants are from Andhra or from other places also?
From other places also, sir.
From other places also.
Other places, yes.
So do you have their affiliation, whether they are students or?
Yes, sir. We are allowing the faculty, research scholars, PG students, and Indian practicing engineers. Mostly students who are willing, they can attend.
Okay.
But it is open to these people. Sir, my voice is clear, sir.
Yeah. It is clear to me.
Okay, sir. Thank you.
So actually, Girish, there will be only one problem. If suppose any power failure is there,
Sir.
okay, my internet will go. Okay, because
Okay.
this is based on the power. It's not the Wi-Fi. Okay. So any problem, power shutdown or like something in the campus, then actually like I will rejoin. That time only I will call you. Okay. So you can inform to the participants. If any issue is there, then I will make a phone call to you.
Hello. Yes, sure. I'll do once. 1 minute.
Normally it won't be there. Sometimes very rarely. Just a few minutes or maybe like some maximum half an hour, they will take it out.
Hello, sir. Hello, sir.
Hello. Sir, good morning, Andy.
Sir, good morning. 10 kana, sir?
Yes, sir. Can we start program?
Yeah.
Hello? Yes, sir. Thank you. I'm can post message in the chat box. Hello. Is audible all participants?
Girish, your voice is little breaking.
Hello. Hello.
Yeah, go ahead, Hari, Girish.
Yes, sir. Yes, I'm going.
Yeah, voice is little shaky, but it's okay. You just go ahead.
These students and professors.
Maybe you can keep your mic a little away from you. Don't keep very close to your mouth. Mic, can you keep little away?
Yeah, sir. Now, sir, is this okay?
Yeah, go ahead.
Dear other participants, other faculty from other institutes, other professionals and working engineers, a very good morning, one and all. Myself,
Girish, can you just stop a minute? Maybe I can talk. Participants, actually, this is Venu Chandra from IIT Madras. Can you be able to hear me at least? I don't know about Girish.
sir, yes.
Others, actually, can
Yes,
you
sir,
just
yes, sir.
confirm
I'm able to hear you.
whether you can be able to hear me? Yeah, then actually, I think
You are perfectly all right, sir.
he's just making some introduction.
Yes.
Okay, so don't worry about that one.
Yes.
I can give my introduction. So this is Venu Chandra from IIT Madras. I am an associate professor in the Department of Civil Engineering, and my main areas of expertise is experimental hydraulics, and then sediment transport, river training works, and then cohesive sediment dynamics, and also I work on hydrodynamics of the mountainous stream flow. So now actually the title of your STTP is like software techniques in civil engineering, but whatever the softwares people are generating, out of all, like you need some data to compare your numerical models, whether you do numerical or maybe analytical solutions, whatever you prepare, but you need some data. So this topic is slightly deviating from the main title of the HTTP, but most of you may not aware like what kind of physical studies we do in the labs in the field of hydraulics and water resources. So I think actually like this topic will be more useful, at least like you will get an oversight how actually like the people at different institutions are generating the data to validate their developed models. Okay, so what normally do is they go to the field and then like they measure some data from the field, and then like they compare their data, or otherwise sometimes what happens, you can collect your field data from by going for a site visit, and then like replicate here, and then create more data for different situations, because you cannot collect all the data throughout the year in the field. So what we do is, So we just bring back the data from the field to the lab, and then we start generating for different scenarios. Then your numerical models are like whatever the codes you are writing. So you can validate those things for this kind of situations. So in that connection, for example, in hydraulics and water research, we use HECRAS. So we use CCIT 2D, or otherwise we use Mike 11. So whatever the models you use, but actually like unless until you have some data, so you cannot validate. So even actually like the models where actually these softwares have been developed, so they already checked with the experimental data. So now any code nowadays you people are writing, or for that matter all the researchers are doing, so parallelly someone has to generate the data. So now for the river models, especially like where you have different kinds of bed, you have the rigid bed and then you have the mobile bed. So my main topic is how to prepare these models instead like to collect the data. So I'll give a lot of equations, but don't worry about that one because these slides will be shared with you. So you can leisurely like go ahead, and then in between if you have any doubts you can write in the chat box, or otherwise like after the presentation anyway. I don't have any time restrictions. Okay, so the time slot given to me is 1.5 hours or 2 hours, but actually like I can be available. So you can put your comments in the chat box, and also after the presentation you can straight away ask as many doubts as you can. Maybe like this topic you learned it in your BTech, but maybe like I will give you a kind of a review for you. It is not like the topic is not new to you, but only like certain equations I am going to emphasize. That's all. So I'm going to share my presentation. So these slides, can you be able to see?
Yes, sir. It is visible,
Yeah.
sir.
Yeah. So the title, as I said, like how we do the physical model studies. So first I can like some photographs I am showing you. So these photographs two I have taken from the field. This actually like I downloaded it from the internet. You can see the reference. So here actually like a breach happened. Suddenly actually like a bank of a lined canal. So suddenly it breached up. And then you can see a lot of sediment in the other thing where actually horse cart is there, and then a lot of sediment is coming in the flood water. So now if I want to estimate what kind of sediment load is coming in that water, and then actually like how this breaching happened. So breaching can happen like due to the overtopping, or maybe like to the through the piping, and then what kind of breaches, because this breach is also like similar to your dam break analysis. So if I want to generate some data for the dam break flow analysis, because most of the dams across the globe, they are all old. So then somewhere either today or tomorrow or like down the line few years later, so you have to break those dams. But actually like breaking is not just like that. So once actually like the lifespan of the dam is over, then you have to smoothly remove from that location, and then without affecting the downstream areas and also the public and the properties. So now the issue here is, so how best actually like you can create the model. So then actually like coming to the bottom, so this actually a kind of construction studies in the river to construct a bridge across any river. Because if you consider like this in the figure, the bottom one you can see. So this figure actually like this entire thing is considered as the width of the river at that particular location where you are planning to develop your bridge. Then we are not going to construct for the entire length unless until actually the discharge is huge. So then what we do is, so we are going to construct, we are providing abutments, and then what happens when you are providing the abutments, then finally you are going to construct your water passes. Then here the velocities will increase, and then like the sediment will washed away. So that means here some flow changes as well as the bed changes are happening. So now the issue here is, so how to get both the flow dynamics and also like the bed variation. So these kind of studies also how best we can do it in the lab. Now this actually is from my voice is audible, like any comments?
No, sir, it's good.
Perfectly all right, sir.
Yeah, okay. So now you can see I am showing one figure on the top, that is railway bridge across the river Godavari. Many of you familiar with this one. The left one is the one constructed by the Britishers, and then right one we constructed after the independence. So now, who has decided the bridge has to come on the right side of the existing one? And who has decided that bridge should be having this much of clearance from the existing one? Who has created the spacing of the two supports or the for a span of bridge? Then actually like it should be this kind of length. So all these questions, and then who has decided what kind of footing you are going to prepare? Because actually like this is a kind of double D arrangement, and then you have the bottom well, and then after that one above the superstructure you have another kind of double D pier. Now you look at the bottom one, it is from the West Bengal, so where actually like bridge across the Ganges. So here very closely so many bridges are there. That means actually like all these supports, they are going to act like a kind of a group of piers. So who decides all these? So then actually like this data or this information or otherwise these suggestions comes from the hydraulic person who does the experiments, and then he conducts the experiment in different scenarios and then find out what should be the clear spacing between these two piers, or like what is the distance from the existing pier. So like that actually like they will give the data, then based on their input, so they design. Then actually like this data goes to your geotechnical engineer, and then like later it will go to the structural engineer. Then all these people work later. So but the initial job is by the hydraulic person. Now actually like here these two figures I am interested to show like the shapes. So one is actually again across the Ganges in Allahabad, the other one is again at the Krishna river. So these shapes also it matters, and also like the alignment matters, and then what is the spacing also matters. So these kind of questions we have to address. For conducting the hydraulic models, so you can go for the physical model, you can have the analog models, and then this chart actually you can read it later. So because actually like the time will be short if I concentrate more on this one, but I'll go for the physical models. So under the physical models, what we have, you have the liquid models and then you have the air models. So wherever the structures, the hydraulic structures we are talking, or wherever the constructions which are in contact with the water, so that actually like we take care. And then the air models, so although the principles are same, but actually the aeronautical people, so they do it. Basically here we are talking about measuring the velocities, we are talking about measuring the pressure, so we are talking about measuring the viscosity, both in liquid models as well as the air models. So we do measure all these velocities, viscosity forces, and then the surface tension forces, and then what kind of friction things are happening there. So all these things we measure in physical models based on our requirement. Then this slide is not very new to you. This actually like you might have everybody studied in your BTech. So that means when a flow is happening, so you are having so many forces. That means viscous force, gravity force, pressure force, so then the elasticity force, and then the surface tension force. So now when it comes to your river models, so you consider the viscous force, gravity force, pressure force, and then the surface tension force. Elasticity forces normally we don't consider, but viscous, gravity, pressure, and then surface tension forces you need to consider. Although actually like you might have studied the gravity force, because the flow is happening due to the gravity. So the gravity force is the predominant force. So you people consider only the fluid model law, but at the same time, so don't ignore your Reynolds number and also the Weber number. So why I'm insisting on this one is the Reynolds number, whatever you consider during your model studies, it should be as high as you can. So don't only focus on your fluid number, your Reynolds number should be very high. And then your Weber number also it should be high. So why actually we are keeping the Reynolds number and then Weber numbers so slightly higher is because, so if I want to neglect the scale errors, then it should be really high. Then this slide, you can see the slide number 8. So where I am giving all the time ratios, the time ratio, velocity ratio, acceleration ratio, and then like the discharge ratio. These things actually like you very well aware of this one, but how to prepare it? Actually, like on the right hand side, so you can see a river model, which actually like it is there at IIT Madras Hydraulics Lab. So in this figure, who decides what should be the width of your model? That actually like if it is a rigid bed model, yes, I can do it. But if it is a mobile bed model, I cannot. Okay. So then what is the procedure? So the question comes here, what is the procedure? The procedure here is, what we are following is, you just leave the bed after leveling it just like that. So I'm not going to touch anything on the bed. So this, excuse me. This particular model, the concept here we developed is, if you have two rivers, both of them are merging together at some location. Actually, this is the location, but the lateral river can join perpendicular or maybe at some angle. It doesn't matter. Then this is your main river. Maybe you can say where Bhagirathi, and then what is this? Many people like who are from this Uttarakhand, so they know like from which point the Ganga starts. Okay, so the Ganga starts. I think one is Bhagirathi. I think there is one more river where actually like both of them join, and then from that point we call it as the what you say the Ganga. So that other river, just a minute, I will tell you. Yeah, Alakananda. So the other one is Alakananda, and then Bhagirathi. So these two rivers, they are joining together. So now actually like what kind of flow changes and also the bed changes happens. So the principle here, what you have to follow when you want to generate any physical models at your institute. So you just level the bed and then just leave just like that. So you are not going to touch anything, and then start allowing the water, consolidate it for about 1 month daily, actually, like, or otherwise if the work is really important and then your time is short, then at least minimum some 7 days to 10 days you just consolidate the sediment by allowing the water. Then you slightly create a kind of channel which is here. So just actually this initially we created some channel, then this side also we created some channel. Just with hand you can create the channel. Then what happened? Slowly, after some time, once you allow the water, the slope scale will be fixed automatically. So here the most important thing is, although you fix your scales, whether it is a velocity scale or time scale or maybe like the depth scale or the length scale, whatever you fix, but when it comes to the mobile bed, the scale will be fixed by the model itself. So here we are not going to fix any scale in the beginning. So first actually like we are allowing the water to flow, and then you are making a small channel, then you are allowing the bed to stabilize, because the river also, it adjusts to its original state over the years. So same thing we are doing it here. Then first thing is you are going to develop the slope scale. So from the slope scale, you go back to the velocity scale and also the depth scale. Now here, what is there in your hand? So your hand, only one is there, that is the length scale. Only the length in the longitudinal direction. So the other scales, the model automatically, it will be fixed. Now, if it comes to the rigid bed models, so what we are going to do is, so the rigid bed models, thus including the surface, you are going to fix it, because everything is in your hand, because you are restricting the water to a fixed area. So then you can decide your scales. But in the mobile bed, we are not going to do that. So we are taking all the scales or calculating based on the model. So then actually like what kind of models we generate or like we work on in civil engineering department is the gravity models, where the examples I have given if you are interested to study about the weir, spillways or siphon spillways. So here actually like where the gravity is the predominant force. So then all these things you can do it. Then there is a sectional model where actually exactly your laboratory width. For example, here this entire width, if you are interested to fix as your section, then that is the spillway models. Then those things, what happens is the velocity in this at each location in the length of the spillway, so is fixed. Then only the velocity is varying only in the 2-dimensional. Okay, so this side actually like you are keeping the same velocity, but laterally and then like the vertically. So what is the velocity variation? So these 2-dimensional flow models like spillway models, you can directly go for the entire section. Those models we call it as the sectional models. Then there are actually like I have mentioned the pipe flow models, and then like the MAC models, the pump flow models, ship models. So here the ship models I am little interested, and then the surge tank models. Here we are using the gravity as well as the friction. So that means, what do you mean by the gravity friction models? So that means you are considering the Froude model law and also the viscous model law, that is the Reynolds number. So both the numbers are equally important here. So that is actually gravity friction models, but it is slightly difficult. I will tell you like how to do that one also. Now, as I told you in the earlier slide, so you need to take the high Reynolds number, high Weber number when it comes to the river models. So now, if you look at this slide, here horizontal scale and then vertical scale I have considered. This actually I will move very quickly. So, you know, like based on the Froude model law, so this is the equation VR is equal to under root LR, and then based on your viscous model law, so you are getting, so VR is equal to nu R divided by 1 by LR. So this actually like is changing. Now if you look at the example here, what I am showing, so if your LR is 1 by 100, then FR is Froude model law, it will give you a VR of 1 by 10. But when it goes to the Reynolds, then it is 100 by 1. So where contradictory things. So it is not very difficult if you are rich enough, and then if you have a lot of funds from any sponsoring agency. So you can use the different kinds of fluids, both in the model as well as the prototype. Then you can create the model. But actually like it is not advisable. So that's the reason why you have to increase your Reynolds number in the experiments. So if you ask me like what is the Reynolds number I use for this kind of model study here, the river confidence model, so then actually like here it is more than 30,000. Okay, so it is like 30,000 Reynolds number I used here. That means the flow is highly turbulent. So once actually it is highly turbulent, then I am neglecting the viscous surface. So that is the basic idea. Now what we are going to do is, so you are going to do only the model testing based on the dominant force, but without compromising on the scale errors. So you should minimize the scale errors. So if you consider the turbulent flows, so I am going for the gravitational force as the predominant force, and if I am going for the ship models, then gravity as well as the viscous forces I am considering. But here there is a slightly different mechanism is there, how to measure the viscosity of the model in the frictional models. Now the other thing is, when it comes to the techniques, what kind of techniques I have to use to go for the model studies. So the first one is, here you have to construct a watertight basin. So this you have to construct, then make arrangements for the flow measurement. So if measure like for me, maybe I can make a little bigger. So I hope this screen is much better. I'm sorry, actually, like you didn't inform to me the screen was short. So anyway, so now here in this figure, in the downstream, we have one V notch, and here one more V notch is there, and then this side also one V notch. And two pipes are coming, and then I can fix a flow meter to this one. So that means for the flow measurement, I am making the arrangement. Then once it is watertight, so what you need to do is you have to calibrate the model. That means whether it is giving the good results or not. Okay, so then once your model is calibrated, and then once you develop the confidence that it is giving the exact results, then you can collect the data from your model. Then what kind of material you can use here is, so you can use the plastics, you can use the acrylic sheets, any fiberglass you can use the wood, you can use the metal plates, you can use the stainless steel, you can also use the wood with a kind of paint, otherwise actually like the wood will get damaged. And then the frictions you have to see when your main dominant thing or measuring thing is the friction, then what is your prototype friction, and then what is your model friction, you have to see. And then if I am using some kind of cement motor or otherwise the wooden material, what actually we do in the lab is we just go and paint it, because in your field, if you look at the Manning's N, the roughness coefficient, so the N is like a 0.01 to 0.03. So then it is very small, and then when it comes to the model, it should be much smaller. Then how to get that one? Then to get that one is, so you just paint it and then make the surface more smoother, what best you can do. Sometimes actually like we do varnishing the things, and then later we do the painting. So in that way, yeah. Somebody raise the hand. Kirti. Rajesh also raised the hand. Anything? Girish?
You can see the box.
I don't know. Actually, like I'm not. I'm in the presentation mode. So actually, like, what is the issue? Can you just look into the chat box and then see why did they raise the hand?
So they are asking us to just repeat that one more time.
Okay, this model techniques.
Yes, sir.
Okay, that's okay. So the model technique here is, so you initially you are going to construct a watertight chamber. Then if it is your the bed is mobile bed, that means where you are putting some sediment, or otherwise the bed is rigid bed. In both the cases, so how to get or how to bring your field N value to the model. So then actually like the N value varies in the prototype from 0.01 to 0.03. Then your model, it should be much smaller. So then in that case, what we are going to do is you make the surface little smoother, and then either you can paint it or otherwise like apply the varnish if you are using the wood material. And if you are using the cement mortar, that actually like definitely you have to paint it. Okay, and then what kind of material other than this cement mortar and then wood, what you can use is for the flow visualization. So what we do is the acrylic sheets or otherwise the fiberglass, because you can really look into the flow dynamics, and also like you can easily measure it. And we use the stainless steel or otherwise some metal plates also we can use it, because where the metal plates you can usually mold it. Okay, wooden things sometimes it is a problem. Then sometimes what you do is, if your main agenda or otherwise main objective of your model study is to develop a model to measure the flow variations, because nowadays the major cities, for example Chennai, 2015 floods happened. Then actually like a lot of inundation happened. Then if I want to forecast for the future scenarios, then I have to go for the analysis of flow variation at the different locations. So I have the survey data, okay, or otherwise I can go for the hydrographic surveys, and then prepare a templates. That means actually cross sections of the river I can take. Then later what I can do is I can create the surface in such a way that the entire rigid bed, including the undulations and then like up and downs, so you can create the model. Then here your main objective is to find out what is the flow. Then you just paint the entire surface. So again, Girish, again 2 people raise the hand.
Sir, we will proceed, sir. They will ask questions in the chat box. No issues.
Okay. Some Venkatesh raised the hand. That's okay. Maybe you can keep all your doubts, and then at the end, I will try to answer. Okay, because now again and again from the presentation to the chat mode, I cannot go and come back. Okay. So you just note down your doubts, and then I will address every doubt. Okay. So then you just, your objective here is to measure the water depth. So you just paint the entire surface and then make it little smooth, because the friction is not the issue for you. So then make it as smooth as you can, and then start allowing the flow, and then measure the flow depths at different locations. Sometimes, so if you go to the field, you are unable to collect the data. So those kind of data, we use the satellite information. Now this is one setup we created at Hydraulics Lab. So here you can see one is coming here. One you consider this as a river. A V-notch I provided here, and then one more V-notch, and then backside pipe is there. I can put a flow meter. Then in between I can generate some keep some baffle wall, so that like I can reduce the turbulence. Then this side you can see a kind of channel, the trapezoidal channel. So which the water is going. That means this channel I consider as the intake canal. So you are drawing the water, and then this idea we got it from Vijayawada, where thermal power plant is there in Vijayawada. So for the thermal power plant, they are drawing the water from Krishna River. So then actually, like, what kind of sediment load it comes to here, which is the problem of decreasing the discharge in the intake canal. So how to minimize the sediment load. So this is related to that study. So then you can collect all the sediment here and otherwise in the channel. Then you also collect the data from here. In that way, actually here, our objective is to find out or to minimize. So what is the sediment load which is entering into your intake canal. So this actually, like you can also read this paper came in AICTE paper. So you can look into my profile and then you can go through it. And then this also like a river model, as I told you, the confluence model. So this also there in my profile, you can check it. So how actually like we prepare the model, what are our scales, then how we develop the experimental setups, everything details you can find it out from the papers. So these are the flow meters earlier I was talking about. So you can fix the flow meter to these pipelines. Nowadays, the price also not very high. So you can easily fix it. But while fixing, the flow meter should be vertical. That means the flow meter, it has to, the water should fill the entire cross section. It is horizontal, and then the water level is half full in the pipe. Then you cannot really get the values. So this is continuously you can monitor from the display unit. Then coming to the river models. So river models, as I told you, you have the two types. One is the rigid bed and another one is the mobile bed. So this figure in the beginning itself I am showing you. So if you understand this figure, the rest will be very easy. And if you look at this graph on the x-axis, your LR is there, the scale ratio. And in the y-axis, so there is a KR. The KR is nothing but your sediment size. The K I am denoting here, but actually, like if you want, you can also write dr, that is the diameter of the particle, where this KR is nothing but your friction. So if it is the rigid bed model, what you can do is, so that is nothing but your roughness, the roughness, and then like the sediment particle. In the rigid bed, the roughness of the bed is offering the friction. If it is the mobile bed model, the sediment is offering the friction. So in both the cases, this KR or the DR is one and the same. Then you can see a C line, and on the right hand side, you have the model, whether it is a smooth model or the rough model. Then this C is a constant. This C purely depends on the flow condition in the field. It is not related to the model, but it is related to the field. So your field data tells you what is your C. That equations and all I will talk later. Then there is another small letter is given, that is the E. E is equal to 1, and this actually like we are having some cross lines. So and C is 1 here, and then C is 0.1, and then C is 0.01 here. And then scales I am going from 001 to 1. That means you are taking, that is actually like if your LR is equal to 1, that means your model length is equal to the prototype length. That is the similar models. So from 0.001 to 1 I am taking here, and then like this is a smooth or rough, and then the C line, which is a function of the flow dynamics in the prototype, and then there is a small e. This e is a function of the depth scale as well as your length scale. Somebody, can you please unmute somebody? Venkatesh. Yeah, so this E stands for the as a function of the depth scale as well as the length scale. Now, how you are classifying your models? So if I am going for the rigid bed models, so your main agenda is to measure the flood levels, or otherwise to find out what is the capacity of your channel, or otherwise you are going to see the propagation of the flood wave. So how actually like the wave is coming. Generally this maybe a dam break flow analysis, or otherwise like suddenly due to some situation, maybe like if the all the dams or the barrages are full, suddenly you are lifting the gate. So then what is the wave propagation? Then the movable bed models, here your main agenda is, so what is the bed movement, and then how much covering is happening, so what is the silting happened. So then you go for the mobile bed. Most of the time, Venkatesh, can you unmute? Yeah, undistorted models we use. We don't go for the sorry, actually like we go for the distorted models. Undistorted models only if your main aim is to find out the turbulence and then supercritical flow, and again waveform propagation, and then how the wave formation is happening. Then you go for the undistorted model. Basically, like the distorted models here is the distorted model. One simple thing is the difference between undistorted and then distorted is the vertical scale ratio differs from your horizontal ratio. So all our models, we go for the distorted models, but sometimes if your vertical scale is equal to the horizontal scale, that is undistorted model. But here, the main thing here with the undistorted models is, here the Reynolds numbers is the issue. The Reynolds number drastically it will come down if your length scale is equal to the vertical scale. So you try to keep your vertical scale different than the horizontal scale, then you can increase your Reynolds number. So once it is the Reynolds number is increasing, that formula rho Vd, that means velocity is high. So that means you are going for the turbulent models, so that you can minimize your scale effects. Now, what best you can do, this slide already I discussed. So what you are going to do is you try to keep the turbulence as much high as you can. Otherwise, so there are two issues. One is the velocities will come down. Once the velocities are coming down, the sediment particles which is there, so it cannot move. So, but actually like in the real condition, the sediment is moving when the flow is happening. That is number one. Number two is, once you create the length scale is equal to the depth scale, then your flow depth in the model will come down. Once actually your flow depth is decreasing, you cannot measure the velocity data properly. So you need to have sufficient depth. Okay, so this is the two important things. These are the things. So you please keep in mind. So then normally, so we use the length scale in the range of 1 in 2000 to 1 in 100. And then the earlier model, what I have shown was that is 1 in 80. So the vertical scale, yeah, vertical scale I was talking. So that was 1 in 80. So for that sediment model. And here I'm defining that actually, like as I told you from the plot, that is the vertical exaggeration, that is the E is a function of depth scale and as well as the length scale. So you can use this vertical exaggeration, different things for different models, but it is not a hard and fast rule. So it can be adjusted as per your local requirement. Then now from where all these resistance formulas have been developed, this is a slight background I want to give. The resistance background initially for the river flow, so we don't have any equations as such. So then the existing equations for the pipe flow. So those equations we started using it for our sediment transport models. So what are all the equations we have for the pipe flow? The hydraulically smooth boundary. Boundary is smooth, but the flow is turbulent. Boundary is rough, and then the flow is turbulent, and the transitional turbulent flow. These are the three things. So we use it, and you know it. 1 minute. Something is coming here. Some box. So you can see like the Darcy's Weisbach equation. So HF is equal to FLV square by 2ZD. Then if you consider the hydraulically smooth boundary, but the flow is turbulent. So you all very well know from the Moody's diagram. So from the Moody's diagram, what we are going to do? So the Moody's diagram tells the friction factor F depends on the Reynolds number, that is one. The second one is the K by D, or otherwise epsilon by D, or otherwise like the epsilon by R, where actually R is the hydraulic radius, and then actually otherwise the hydraulic diameter, or otherwise hydraulic mean radius, whatever you call. So then actually like this D you can see, or otherwise epsilon by R, but that epsilon talks about what is the roughness. Okay, so generally what happens, if you see the roughness or any broken pipe is there near to you, so if you just touch the surface, there are small bubbles are coming up. So it is having some kind of undulations like this. Then you take the mean value of the projections of the roughness. So that tells you what is the equivalent roughness. So that is your K value. So my roughness thing, friction factor, depends on both the epsilon by D, or otherwise epsilon by R, or otherwise the Reynolds number. So these are the two different things for the smooth, turbulent, or the transition region. Then in the box also you can see different kinds of material. So for the steel, and then motor lined steel, rusted, then water mains, old pipes, and then like the concrete, or otherwise the bed is smooth. So you can see all kinds of ranges here. The same thing, what we are going to do is, so these things we'll use to develop our mobile bed models. Now in this slide, the other equations you know it from your basic fluid mechanics background, but you just try to concentrate on equation 1, which is given in the bottom. Here in the center, I am saying the Reynolds number should be higher than or the greater than the turbulence Reynolds number. So you try to remember these subscripts. RE stands for the Reynolds number, and then RT stands for the turbulence Reynolds number. And here the Reynolds number is there in the model, and Reynolds number is there in the prototype. But both the cases, your Reynolds number should be greater than the turbulent Reynolds number. And this turbulent Reynolds number is a kind of empirical formula. So this actually like we can get it from the above equations. So the RT is 800 divided by F stands for the friction factor, and then K stands for your particle diameter, or otherwise surface roughness, then R stands for your hydraulic radius. So then from here, so you can get it. That means the turbulent Reynolds number, so it is a kind of function of your friction and also the particle size or the roughness, then your hydraulic radius. So I am giving everywhere the equation numbers. So you try to use those things. Once you finish the lecture, if you want to solve some problems, so those equations you can recall. Then initially, so what I have to do is from this figure, so the main thing what I want to tell is you take the LR, you take the KR, and C and E are there. Now for all these scales, what I have to do is I have to generate some kind of equations. What is the equation for the upper limit? What is the equation for the lower limit? So once I know what is the upper and then lower limit, what I can do, if suppose my KR upper limit and lower limit is, this is the lower limit and this is the upper limit. So that means I should be in this range. Then my LR is from 0.005 to 0.01. Then actually like I should restrict here. So that means my area is coming here, Then what is my E, vertical exaggeration? Then this also I am fixing. Then what is my C? So whether I should be in this range or above this or like below this, then I am fixing a kind of region where from that particular box, after fixing the boundaries, you select your LR and then KR to get the good results. So now our job is to find out what is the upper limit and then lower limit. So this Manning's formula, Chedji's equation, this and all, you know it very well. Now this N stands for the Manning's roughness. So this N, how to find it out? So this N, once I like you use these equations, so this you are getting the equation number 2, and then for rough boundary from the pipe flow, I'm taking this equation. Okay. Now, if for different values, if I fit the F and then like R values, then I can get a kind of power equation in terms of equation number 4. So this power equation for the friction factor, if I substitute in this second equation, slowly I'll narrow down to a equation N is equal to K to the power of 0.167 divided by 26. So this is your equation to find out what is the Manning's N. And the same equation you can use it if it's a rigid bed model, what is your friction, the roughness here you can use, and if it is a sediment transport or the sediment you are using as the bed, then that equivalent or otherwise the D50 value you can use it. If you are using D75, then actually like this now denominator will change. If you use the D50, you can use as the D50 in place of K. So that means my N value I am getting. So like that, so we are going to develop certain equations. If you are using sand or gravel bed, then actually like the D should be, it's not exactly the D50, it should be as the 75% finer. And then if this is actually like the D50, if you are using, then actually you use the 24. Okay. So I hope actually like I'm not going a little fast. So when it comes to the equation, anyway, the slides will be with you. So you can leisurely, you can read those things. Now, as I explained earlier, the most important thing is to find out the turbulent Reynolds number of the model as well as the prototype. It should be always higher than, sorry, your model Reynolds number should be always higher than the turbulent Reynolds number. So now, why we are using the distorted models and then the turbulent Reynolds number is very simple, as I told you earlier. So you are going to maintain the turbulent flow in the model that will help you to make your sediment to move. So it means the bed shear stress is going to be maintained. The third one is, if you maintain in this way, you can get the sufficient depth so that you can get the velocity measurement, and also you can increase your velocity for the bed movement. These are the things. Now the bed models, rigid bed models, then how actually like you are going to use it. The same thing you will use the rigid bed models. The same plot which I discussed earlier, same plot I am showing. Now you see the Reynolds number of the prototype I am considering initially. Then the Reynolds number of the prototype I am writing, where actually like 4yp is nothing but your, what is this one, rho Vd by mu, and then here actually like I am considering as the nu, where my D is the 4 times the depth of the flow. That actually from where I got, from the pipe flow. The hydraulic radius is equal to A by P, wetted area divided by wetted perimeter. From there I got this one. Then I know my Kp is 26 times Np to the power of 6. This I got from the earlier equation. Then K by Y, I can fix it. Somebody, can you please unmute? Sorry, you please mute yourself. Please mute yourself, all of you. Okay, so then I have to check my Reynolds number of the prototype is higher than my turbulent Reynolds number or not. So this is the equation we have. Then sometimes the equations like this, so these are some thumb rules. Actually, like based on the previous experiments, people have developed certain thumb rules. So out of that, so this is one thumb rule where actually like your top width of your model or the prototype, the top width and then like the depth of the flow in the model should be always greater than 10. So this is only to avoid the experimental difficulties. This is to avoid the experimental difficulties. So now, once actually this you know, from the vertical exaggeration equation, you can write this. So from here, I'm getting, so if I consider this as the 10, then E max, one limit you are getting as the 0.1 times T by Y of P. So that means, so the E, one value you are getting, the top width of the prototype, you know, the depth in the field, you know, so you can calculate that one. Then the other one is, what should be the minimum depth of the flow in the model? Normally we always keep greater than 5 centimeter, but the literature says you can go up to the 3 centimeter, but provided to measure the velocity, you have the sufficient latest equipment. That is, if this kind of depth you are considering, then the velocity measurement should be done with the laser Doppler velocimeter, where actually you are not really dipping any instrument in the water. So generally ADV also you can use acoustic Doppler, but acoustic Doppler you need more than 5 centimeter water depth. So the laser only you can get velocity at whatever the depth you have. So now if I keep this as the thing, then the LR minimum I am getting 1 limit, that is the minimum limit. Then what should be your model roughness? The model roughness should be 0.0005 and 0.01. Between this range only you can select your surface roughness. So that means automatically I am fixing the model and then the prototype things, what is the roughness. So that means KR minimum and KR maximum. So what is there on my Y axis? I got the limit. Now what is the LR maximum? The LR maximum, there is no limit, because from 0.001 or whatever the LR minimum you are getting from this equation till 1 you can get it. So that maximum limit is 1. So it all depends on what kind of scales are like space available in your lab, and then what is the water availability in your lab. Based on that one you can fix your LR maximum. So what we got, LR we got, that means x-axis we finished, so we finished the y-axis also, and then E max we got. Then you will get a kind of E minimum based on your Freudian model law and the frictional model law. For the frictional model law I am using the Manning's equation, and then Freud model law I am using the Freud number. So using these two and then substituting the vertical exaggeration is nothing but your depth scale divided by L scale. Once you substitute everything, you are getting a kind of E minimum, provided K by Y of M, it should be in the range of, it should be less than 0.2. So once this is a thumb rule, so 2 thumb rules I have given, 1 thumb rule here, and then there is 1 more thumb rule. So then once you follow this, then you will get a kind of E minimum. So E minimum you got, E maximum you got, then KR minimum you know, KR maximum you know, then LR minimum you know, LR maximum you know. Then what is the C value here? As I told you earlier, the C value purely depends on the Reynolds number of the prototype. That means prototype field values only you have to use to get the C value. So now I am considering the Reynolds number and then Reynolds model law. Then from there actually like I am getting the YR to the is equal to Reynolds number ratio is equal to YR to the power of 1 by 5, and YR is E multiplied by LR. Then Reynolds number of the model should be greater than turbulent Reynolds number. Then that equation I am considering. Then actually like here RER also should be later than this one. Then I am using the equation number 2. Then from here, then I can straight away get equation for the LR minimum in terms of vertical exaggeration. Then this vertical exaggeration, after eliminating that one, and then whatever the factors or the equation is there, this is my C. So getting C is very easy. Now you see like Reynolds number of the prototype, you know what is the field velocity, you know what is the hydraulic radius, then you can get it. and then there is only like some coefficient is there 177, and K is nothing but your field particle diameter, and then Y is the depth. So you can calculate what is the C value. And how to use these equations also, I have given two different examples in the same presentation. This will be shared by Girish later to you. So then actually like we can go through that one. And I have given the examples how to solve those things. So C value is there. Now everything you got it. This actually some supplementary equations, you can go through it. Now C value you know, LR minimum you know, LR maximum you know, KR minimum you know, KR maximum you know, E minimum and then E maximum also you know. Now somewhere here you will get a kind of box. So I'll show you, this is the example, and now this is solution for that one. Now carefully you look into this one. This is my LR minimum, and then this is my LR maximum for the example given in the previous slide, and then this is my KR minimum, KR maximum, and then I am considering one E. So E minimum and E maximum is there, but actually like I am fixing my E as this one. Then these are my boundaries. Now I fix the boundary from E1 to 3.7. So I am fixing my boundary as the this one. So now here I selected this point, but you can select whatever the point you want. And then C line is coming here. So because C is 0.001 here, this is 0.1, and then this is C is equal to 1. So in this problem, what is the C value I got? C value I got 0.11. So 0.11 is coming here. So this is my C value. So I hope actually like you, if you have any doubts, you just remember. Then actually like I will also address later. Then once you know, so here the KR values or KM, then actually rest is how to find out your scales. Ultimately, our main thing is for my model, what should be the discharge? What is my length ratio? What is my depth ratio? So I'm getting the length ratios, depth ratios, and also the discharge ratios. So this is the thing like for the rigid bed. Now mobile bed, you have slightly a kind of different approach. The mobile bed, what you have to consider is, so you have to consider the densimetric fluid number, or otherwise we also call it as the Shields parameter. So you have to consider the Shields parameter as the one of the important thing. And you know like gamma R S naught, this equation you have, you know it from the open channel flow, that is to find out the bed shear stress. So you can use the gamma R S naught, but actually here SF we are considering the frictional slope, not the bed slope. You know it very well from the basic hydraulic engineering, how to take the frictional thing. So for the Manning's equation, for the unsteady flow, you consider as the slope of the friction slope. So when you want to find out what is the length of the backwater curve, so that is nothing but your frictional slope. It is not the bed slope. Now the densimetric fluid number, here actually like this is the specific weight of the water, specific weight of the sediment, and then V star is the shear velocity, and then G is the acceleration due to gravity, D is the diameter of the particle. So now this should be in the range of 0.056 for the incipient sediment motion. That means it should be minimum of 0.056 in order to make the sediment in your model should move. That means you are creating the actual field scenario. Okay, so these equations are just a repetitive thing. You can just go through it. It is yeah, it's easily understandable. But here, what I want to emphasize is, so I am talking about the Reynolds number, some star I have given. The Reynolds number star, nothing but the particle Reynolds number. So here you have to use the particle properties. That means the D means the particle diameter. Then it should be greater than 70. It should be greater than 70. This actually like I have given here. But in any case, it should not be less than 4. So these are certain values we should remember. So it should be greater than 70, but in any case, it should not be less than 4. So that is one condition. Then there are 4 different kinds of approaches are there to find out what is the particle diameter. So once actually you are talking about the sediment particles here, because the earlier equations, all the equations are applicable for the mobile bed also, but only difference is there the friction means the bed friction, but here the particle friction. So the particle friction means you have to find out what is the diameter of the particle. Diameter of the particle in the prototype, you know what should be the diameter of the particle. In the model you should get it. So for this one, so we have the Freud criteria, and then Reynolds criteria, friction criteria, and then there is one more criteria, the shear criteria. So if you look at the Freud criteria, so that means the Freud number should be equal to 1. That means it should be same in both the cases. Then this is the equation I have. So then actually like from this equation, so the R I am taking as the YR, and then this S is nothing but your what is the change, that means height divided by horizontal length. So that is the slope. So then YR by LR, and then this actually like I am considering as the del multiplied by this rho. That means you are talking about the density of the sediment and then water ratio. So that I am considering multiplied by dr. This actually like I am getting from here. So once you use this equation, okay, and then this equation, that means the density fluid number equation, and this equation, you will get here like this. Then from here it should be anyway equal to 1. Then my dr is the only unknown. So this yr by lr is nothing but your vertical exaggeration. So I am bringing in terms of vertical exaggeration and then the density ratio. So why actually like I am giving the densities here, the important thing is sediment density, you know. If suppose I am using a coal dust in the model, I am not using the same sediment particles. I am using the coal dust. If I am using the fly ash dust, then actually this density and then that density is different. So I am taking the equation in terms of the density ratios. So then this is the Freud model. There is the number 1 equation. Then Reynolds criteria, the same equation, Reynolds number you are using. Then you are developing one more equation, that is the dr for the by considering the Reynolds criteria. Then you have the friction criteria. So the third one is the friction criteria. So this friction criteria, you have this equation k by y of r is equal to e cube. Then you are creating one more equation. Then actually like another equation we develop, that is based on the fall velocity, the settling velocity of the particle. This actually like normally we don't use, but it should be used. Okay, so the fall velocity is the shear velocity, you know. This actually like ws stands for the fall velocity. So maybe you might have studied what you call the Shields thing, or otherwise maybe you might have studied the settling velocity, the Stokes law, the settling velocity of the particle. Those equations you can use it to find out what is the WR. So here actually like this is nothing but your Stokes equation. Then based on the Stokes equation, I am developing one more equation for the dr. So here how many equations we have? One is by considering the friction, by considering the Freud, and then the Reynolds model, then the settling velocity. Then actually like for this one also I have given one more example. And other than this one, I have given 2 additional questions to Girish. Maybe he will share those things with you. Later you can solve that one. They are very simple. Just actually like those kind of questions, we just give it to our BTech students, to our MTech student. So I think you can also use those things to solve or to understand these things. But actually like most importantly, you try to understand the examples what I have given after the each model preparation. So then definitely you will understand. Girish, can we go to the discussion mode now?
Yes, sir. Sure, sure.
Just actually like Yeah. So now actually like maybe you can unmute them.
Yes, sir. Participants can talk
Yeah, there are
now
so
one
many
by
people
one.
raise the hand.
Sir, there are some questions in the chat box, sir.
One minute actually
Yeah, you
like
can raise the hand. We can call your name. That is also fine.
uh, yeah, chat box. Yes, sir. So kindly circulate the PPT to everyone. Yes, actually like this PPT it is shared. So don't worry. How
Yes,
do
sir.
you select? You said in more the design capacity school. Actually, like here somebody asked RKV. So this actually he is talking about the Manning's N. The question is depth of water above crest will be function of Manning's N. Yes. If N is simulated on higher side, because actually like here model N actually we are not simulating on the higher side. So that's where actually like I said the N should be as minimum as you can, because in the field end itself is very less, so you have to make it little less. Actually that's where I said you try to paint your model so that like it will become little smooth. Once you prepare the model with mortar or with some other material, then it will be highly rough surface. So that rough surface you have to smooth yourself. That is one. And then what is the role of simulation in physical model studies? Yes, actually like the simulation role here actually it is nothing is there, because you are developing the models to generate the data. That data will be used for the simulation to validate your models. Because for example like now I'll give an example. One is you have developed a model where you want to find out the inundation of a particular city. Okay, so when I was in Germany, actually, like for the Calfia city, we developed some kind of inundation things, and then currently, actually, one of our colleague also here working on the inundation models. Then what we do is we just create the surface smooth, rigid surface, and with some undulations. Okay, depends on the geography of the city. Then what happens? You just start releasing the water. Then at different locations under certain discharges, for example, you take Chennai. Chennai, we have the Adyar River. Due to Adyar River, a lot of inundation happened in 2015. Even the entire airport also, it was under submerged condition. Now, what is our job is, we create a model, then that kind of discharge, we are measuring what is the depth of flows at different locations. Then that depth, I generated a kind of program where for different scenarios, I need to find out what is the depth. Every time I cannot do the experiments. So for certain things, I did the experiments for the limited discharges. Then using my model for any discharge. If suppose actually like tomorrow, the IMD people, they said like next 2 days, heavy rains, heavy floods will come in so and so area. Then actually like suddenly I cannot go for the model studies. It's a tedious job. If I have the model, the numerical model, then what I can do is my numerical model, I validate with my experimental things. Yeah, actually like, yeah, choose the turbulent model in fluent. Actually, I will tell you answer later. So then actually like you generate the model and then validate with your experimental, sorry, your numerical thing, your program is validated. So that means basically I'm validating my developed numerical simulation with my experimental data. Then actually once it is tested, now actually like all the COVID vaccine testings are happening. Why human trials are happening? They are taking sample of 50, 100, and then in India we are taking 1200. The reason is once actually like you generate the vaccine, you are testing it. So once it is tested, you can use that one for any scenario. Then your program is ready, and then using nowadays high quality computers, the programming speed is very fast nowadays. So high-end computers you can use, and then immediately you can type your data and then give the input to that model, and in a few hours you can get the information. Then actually, like from the field survey, you know what are all the depths at different locations, and then all the inundation areas, you know it. Then those inundation areas, you can give the warning system to those people, you please evacuate from those areas. Then actually you are passing on the information to the district collectors, you are passing on the information to the MROs, the local administrative body, and to the government, so that immediately they make the arrangements. Now actually, like if you take the Polavaram dam actually, which is under construction in AP, so that dam actually, like how we identified, there are so many villages of people, 1 lakh people are there in the upstream. That actually, like based on our model studies only. So what is the maximum water depth you are going to keep it at the Polavaram dam, and then what is the backflow? So based on that one, actually, like we fix certain locations. Yes, actually, like all these from the survey data, we say that these places will be inundated if you construct the dam. So that's why actually, like there are RR activities are happening now there. I hope I explained. So then actually, like the fluent thing somebody is asking. So the fluent, I just supplied the data. The fluent, one of our student used it. Then what he has done is, so in the fluent, how actually like they use is the energy variation. The energy variation, that means what is the basic energy dissipations are happening. Actually, like I take a model. So here what is the energy, and then here what is the energy. So from where I am getting the energies based on your specific energy. So that energy variations. So that energy variations will give you the what is that turbulent change. So the turbulent changes you can solve it using your fluid. Any other questions?
Two more questions are there, sir.
Yeah. Otherwise, actually, like maybe later you can, if you have any doubts, you can also write to me. So this is my ID. Okay. So then maybe if you want to write to me personally, if you have any doubts, you can also write to me. No issue.
There are two questions in the chat box, sir.
Chat box, I am there only. What are they? Yeah, for desilting basin or decanting basin, which model has to be adopted? Actually, like this year, you have to go for the mobile bed. Then
what are the advantages of
zero equation turbulence model? Actually, like this, I don't know. Okay. What are the advantages of zero equation turbulence model used in prototype? Actually, like, can you little elaborate this one? I didn't understand exactly what is the question. Zero equation turbulence model used in prototype. Zero equation, you are talking about the what is this prototype turbulence Reynolds number you are talking?
Might be Ganapati Prasad. What is your view? It was asked by Ganapati Prasad.
Yeah, Ganapati Prasad. Actually, like the model preparations, why we are considering the turbulent models of the model as well as the prototype, it should be always higher than the turbulent Reynolds number, is because to minimize the scale errors, to minimize the what do you call to maybe to minimize the scale errors, and then also, like, yeah, as I told you, like the depth scales, you should get sufficient depth scales, so that you will get flow depth little reasonable to get the to measure the velocity. I don't know, actually, like if that is the question you are asking, I hope I answered earlier also. Or otherwise, a little elaborately, if you want to ask, maybe you can ask.
There is one more question on numerical simulation.
Where is that?
The last is it.
1 minute. For numerical simulation, what would be the recommendation length? No, actually, like this, You see, the length fixation is kind of trial and error. I will tell you. Recently, what happened? Like we have used the ANSYS software, and then we have done some experiments, and then we communicated to the journal. So the question we received was, "What is your mesh size?" So it should be little smooth mesh. That means the size is small, or the medium, or the larger. So what you have to do is you have to do a lot of simulations by considering your mesh length. Then later, so you have to come to a conclusion. So this actually, like, I cannot tell what is the thing. It all depends on problem.
So two people raised their hands. If they have doubts, you can
Yeah, I'm
make
seeing that chat box. So chat actually, like, I'm not getting anything.
RBS 31. Actually, you raised a hand. If you wanted to ask something, you can ask question. Unmute yourself and talk if you wanted to ask anything. One more participant, Sahiti, also raised. You can also ask anything if it is there. I think they can ask through mail also, sir. As of now, it is
No
okay.
issue, no issue.
Yes, sir. Very much thankful to you, sir, for your very nice informative session.
Okay, thank you.
Definitely, it will be very useful to all the participants. Yes, sir.
Yeah.
So actually, there was some technical issues from my end. Actually, it was very fine before, but today, I don't know, something wrong with my side. So
No,
it
now
was so
your voice
unfortunate.
is clear. Now it's okay.
It's okay. Yes, sir. I'm once again thanking you for this accepting this invitation from AICTE sponsored this HTTP program to be part of it. And we were very much thankful to you once again, sir, from Sri Vishnu Engineering College for Women.
Yeah.
Yeah. See, somebody is raising hand. If at all you have any questions, you're free to talk now, or else you can pose. Sir can address. Okay. Sir, I think that's all, sir. We will close the
Yeah.
session. If at all anything is there, I will post your mail ID also,
Sure.
so that participants can mail you if at all they have any queries.
Sure. No.
I'll share your PPT at the end of the program, sir.
Sure. Sure.
Right, sir. Thank you once again from our college for accepting this invitation.
Yeah.
Yes, sir.
Thank you.
Yes, sir. Yeah, I have posted participants. I have posted feedback link. Please kindly fill the feedback link which is provided in the chat box. That will really help us to improve. I have one more to say, like we are organizing one conference in the month of October. I request all the participants to aware of that conference, and you can apply for that and post your research work. All the faculties attending this webinar, this AICTE short-term training program, are requested to apply for conference as well. I'll be posting a website also. If you find this is suitable for your article, your work, kindly send us your papers. I have mentioned a website in the chat box. Kindly go through it. I have posted a website of our conference in the chat box. Kindly go through it. For any queries, you can contact us through email. So once again, share the feedback form. If at all anybody misses, kindly give your feedback. As well as kindly go through our conference website. If it is suitable to you, please, without hesitating, you can register and apply. Today afternoon session will be at sharp 4 p.m. By Professor Nagesh Kumar sir from IIC Bangalore on ANN for hydrology. Is one of the topic that will really useful for all of us. Yeah, same link. Yes, it is same link. You can use the same link for entire program, all the sessions, and follow the timings which we have mentioned in the brochure. every day morning 10 to 11:30, except tomorrow we'll have a session from 11 to 12:30. All other sessions are from 10 to 11:30 and after evening 4 to 5:30. Thank you. Kindly go through the conference website. If at all you have any queries regarding registration, attending, presenting article, you can mail us. We are happy to clear all the doubts. I'll provide the PPT, and also we are conducting an assessment in the final session of the program. So in that assessment, we will ask these two questions, which is given by our Dr. Venuchandra sir. Also, a few multiple choice questions also will be asked. I kindly request all the participants to take part in giving your in taking assessment, which will help us to provide you certificate. Yeah, I'll definitely once again keep the schedule. Many of us, few people of this session may not be registered. For them, I kindly request to go give you a feedback so that we'll have your mail IDs, because it is very difficult for me to save your mail IDs here. But anyhow, I am saving the chart. I'll go through once again, but you can help me out by saving my time. So please give your feedback so that your email will be saved by default. Thank you. I think this is all about I think this is all for today for the session. We'll soon meet in the afternoon session at 3:50 p.m. Thank you for attending our AICTE sponsored STTP program for the first session. Have a good day. I see a lot of participants here, over 200, but I received only 168 feedbacks. If at all anybody misses, I kindly request once again to give your feedback. Then only you will have your mail IDs, even if you are not registered also. That will really help us to send you PPT, all sessions PPT. Please give us feedback. I'm sending you again, once again. Thank you, sir. Ram, thank you. Yes, you can leave. People who have given feedback can leave now. If at all anybody misses to give, kindly give and see the information. Feedback form not received. Again, I'll send it again. Just see that feedback link in the chat box. Kindly give us feedback. I'll mail definitely. I'll mail all to the registered people as well as people given feedback. If at all anybody misses again, you can write back us. Maybe the PPT I thought of sharing in the end of the session, end of the complete program, but since we are conducting an assessment, so this PPT share will be useful to you. Just have a look and just rewind. So I'll send it by today itself. Whatever we receive the material from the experts, at the end of the day, we will try to provide. Yes, thank you. Yeah, right. I think this is done for today, this session. Thank you. Once again, have a good day. Yeah, recorded video. See, we actually provided a YouTube link also. If you can subscribe our department channel, for lifetime, those videos will be available anytime, anywhere you can access. Kindly do register our department website. So those videos will be available all the time. You can even download also. Yes, people given feedback can leave the room. Yes. Yes, we have another session in the afternoon at 4 o'clock, 4 to 5:30. So kindly join back at 3:50 p.m. I hope everyone gave the feedback. One last time I'll post the feedback link. You can use it. Kindly visit our conference website and participate. Thank you one and all, and have a good day.